Okay. All right. Yeah. First off, thank you for inviting me, Amir. It has been really helpful to step aside from the ivory tower from a little bit and hear about how people in the industry are using large language models. To everyone, hi, my name is Min Kai Den. I'm a PhD student at Carnegie Mellon University, working on machine learning, computer vision, and natural language processing. And today I'll be talking about optimizing large language models using reinforcement learning. Uh, so from our previous talks, it has become pretty apparent that uh, like even in a bunch of applications, prompting is very important. So I'll be talking about them today. And we also know that these models have been able to be very successfully performing various tasks from asking factual questions for ChatGPT to like chit-chatting with the Lambda model. And in all of these cases, we have it that we're inputting a prompt into a large language model, and it can perform various kinds of tasks depending on the prompt, from summarization to generating code to sentiment analysis to engaging in dialogue or translation or even generating a coherent story. Not sure if it's too good yet, but they surely can do something. Uh, but in all of these cases, these models can be sensitive to how these prompts are worded. Let's take summarization as an example. So let's try some prompts.
Sorry,
Uh,
Minkai.
uh-huh.
There is a Google Meet message in front of your screen. Do you mind clicking on hide on it?
Okay, I'm not sure.
At the,
Oh, do you mean like the height here?
yeah,
Yeah,
that one exactly.
there you
There
go.
you go. Thank you.
Okay, all right, thank you. Thank you for pointing that out. Yeah, so let's try this example. Summarize this article. Sometimes like even with and sometimes even with this pretty reasonable prompt, sometimes the model might not work. So it's disappointed. What if we try another model? The summary is. Sometimes it might just magically work. However, it doesn't seem to make so much sense because these prompts basically mean the same thing. So this brings up the question here of what's really the best way to talk to these large language models. And uh, if we are being more intentional, how can we make large language models do what we want them to do? So this comes to the point of how to find the best prompt for the task that you want to complete. So let's go on with the example of summarization. So now we go back to this previous prompt that doesn't quite work. How are we going to, we know that this doesn't work. How are we going to find one that actually works? The first most straightforward option is to do manual design, which brings up to the job of the future AI prompt engineer. So you can totally hire a prompt engineer here and try to tweak this prompt or coming up with different options. Uh, you might be able to change a word, run it through the model, and see if you like the results. Say this one doesn't work. What if we change another one? And what if it still doesn't work? So we can see that it's sort of an iterative process that's heavily based on human intuition, and this can also get repetitive really fast. Uh, and also it seems that there are also patterns to how these humans are experimenting with these prompts. So what if we let the human step aside and try to use a machine to enumerate these prompt options? So instead of have a human try it one by one, we have a machine that tries to enumerate a number of prompt options by paraphrasing the original prompt or editing it slightly. So we have a bunch of these candidates. We can pass each of these candidates through the large language model and then score them based on the downstream task performance using some measurable performance metric. And based on that, we might be able to select the best one. However, we can also see here that however we paraphrase or edit it, it will still be based on some kind of rule or some kind of heuristic about how by heuristic I mean basically intuitions about what is a reasonable edit that can improve our current prompt. So we're still limiting ourselves to the space that humans typically consider. And often this might not be able to give us a good score. So one alternative to like moving in like the space that humans typically go into and try to explore all the possible options out here is by what's called numerical tuning. This is based on the observation that to a large language model, these prompts are actually not prompts. They are not words as they normally mean to human beings, but just a bunch of numbers. So instead of tweeting all of these words, why don't we just tweet the numbers that are supposed to represent these words? So let's start from somewhere. For example, we have these number of random initializations. And we, instead of passing these words into the model, we pass these numbers into it. And for example, we might still get some measurable score, but we're able to use the neural network of the large language model to backpropagate all of these potential information on how to change these numbers to best maximize our score. And based on that, we might be able to change the numbers slightly, which might improve the score. Like now we get a better score, and we can iterate this a little bit more to get even better results until we come up with something we're satisfied with. So this has been like a prompt engineering method that works pretty well so far, but it also comes with its own limitations. So now consider this: we want to deploy this model, but how do we? But how are we going to get some idea into what's what this prompt even means? And but this prompt is really difficult for a human to look into and understand what it means, because the human can see the word, but it cannot understand these numbers. And also also the whole process is heavily dependent on having access to the underlying neural network of these language models. Say, what if you try to do this to like ChatGPT or like just any OpenAI product? It's practically impossible, because OpenAI doesn't allow you to access their underlying model. It just gives you an output, and you can't even really give these numbers to that model in the first place. So this type of method, while it works pretty well on practice and builds on works well on models that you can have access to, and builds on like years of progress in deep learning, it has pretty limited applicability. So based on this, our research group developed the solution that tries to unify the advantages of all of these previous methods. In that we're proposing this framework called RL prompt, which is optimizing these three text prompts with reinforcement learning, collaboration between Carnegie Mellon, UC San Diego, MIT, and other universities and companies. And our work has already been published at a peer-reviewed conference. And so what our method promises is one that's automatic, so no need for human involvement, at least not as extensively as prompt design. Also, that it's systematic. So instead of basing our optimization process on some intuitions, we are based on a principled optimization approach that systematically looks for the best solution instead of constant guessing. We are also accessible in that we can work with a bunch of different kinds of options. Our framework can work when we have access to the underlying model, but we can also work even if we are using like a remote API like OpenAI, whereas a lot of previous methods weren't able to do that. We're also flexible in that because we're doing a reinforcement learning, it's flexible to design some of our objective functions to reflect the complex tasks that we want to perform using these large language models. And also there are a bunch of design options that will be available, which I can talk about later. Our prompts, the prompts that we find are also transferable, because if we look back to these, I think it's, yeah. If you look back to these numbers here, these numbers belong uniquely to these single language models, because each language model has unique numbers that represents these words. So when you learn these prompts from a single language model, you can't really use it on other ones. Whereas our prompts have been optimized in the text space, so it's actually text, and we can just take it and apply it to other models very easily. Let me go back. Last but not least, our prompts are transparent in that it is relatively easy. It is easy for humans to look into the prompts that we learn and get insights into what are the best instructions for a language model to perform these specific tasks. Let me quickly go through our approach here. So how are we doing this optimization? To talk about our approach, I want to take a step back and talk about the problem of prompt optimization a bit more abstractly. Being more abstract help us to analyze the situation and get some insights about what's the best way for us to solve this problem in the best possible way. So let's say now we have this prompt and we have a large language model. Typically, we will combine it with some kind of input to get an output. And based on the output, we can score it based on some measurable metric. And our goal here is to maximize this score by tweaking the prompt. However, this problem is actually pretty difficult. So imagine this prompt just consists of five words. However, in a typical large language model, each of these words can have 50,000 options. And if we multiply all of them together, in total, we'll have like this humongous number of candidates, which I'm not even going to like say. But it's what it is at the same level with the number of stars in the universe. So this is a really difficult problem to optimize over. And that's why previous methods have typically been like using intuitions to quickly narrow down the search space into some spaces, say, like humans typically consider to be a valid instruction to another human. That might not always work so well for a language model. However, because the space is so large, we're kind of pigeonholed into these spaces that we that to make these problems a little bit simpler, but maybe not the most optimal. Or we can just go through the space as like numbers instead of words, but that also has a bunch of disadvantages, which I already talked about. So to address this problem, we propose to formulate this as a reinforcement learning problem, where instead of iterating over all of these words at the same time, like word by word, we're training a prompt policy that will learn the correlations between these words and their underlying and the score that they will lead to. In this case, in the reinforcement learning cases, can also be called a reward. And after we sample a bunch of words as a prompt, we can run it through the model to get the score. And after that, we call it a reward, and we use this reward information to update our prompt policy. After that, so what this will be is essentially that our prompt policy will tend to repeat the words that lead to higher rewards and downvote the words that lead to lower reward. So that as we sample these prompts again and again, we will get closer and closer to the prompt that leads to the optimal reward. So far, this has been a more high-level illustration of our framework. So I can quickly go through a concrete overview of the entire process. So because previously we said we're using the neural network to learn the correlation between words and the reward. However, this is still pretty difficult. So we also use a smaller language model that is not the large language model that we're prompting to help us understand the correlations between words themselves. So that when we know the correlation between one word and the reward, we also know the correlation between all of the similar words and the reward. To do that, we will insert a small neural network into a small language model that's very efficient for us to train, and we try to we sample these prompts. Afterwards, we feed these prompts into the large language models that we actually want to use, and we'll use that to perform all kinds of tasks. After that, we can compute how desirable our outputs are, and as a reward function, and use that to optimize the small neural network inside the small language model. And we can iterate this process over many iterations, and we will eventually converge to a good prompt that we want. So to better illustrate how like our framework actually works in practice, I want to talk about some experiments that we did to verify our method, as well as presenting some example use cases. So our method can be used for few-shot text classification. So some very famous examples are sentiment and topic analysis. We also experiment with unsupervised control text generation. That is, if you have like literally no training data whatsoever about what you want to achieve, how can you do it? One example here is that is typical for this type of experiments is called text style transfer. It's the equivalent of rewriting Shakespeare into modern English, or like turning something maybe with a positive mood or negative mood into a positive mood. Say here, down here, like we have an input, food is disgusting, and our goal is to have turn it into food is delicious. I mean, that's just an example. Not to say that we want to do this in practice, but it's good. It's an illustration. And I will quickly, and also for these tasks, we will design the reward functions for each of these tasks. So here are some guidelines that we adopt when we go about these. So when we have some training data, in the case of classification, we can use the training data to design rewards. Or if we don't have any training data, but we know how to measure the success, we can develop a metric to measure that success. The advantage here is that whatever objective you want to optimize for, and as long as you can measure it, you can optimize for it. And in the worst case scenario, which we haven't encountered yet, but even if we have no idea how to measure success, it is possible to learn the metric to approximate human judgment. Typically, that happens as in the case of you give a human an input output, and a human can say this is a good output, this is not a good output, and you can train a model to predict whether a human will think this is a good output or a bad output. This is actually the algorithm behind ChatGPT and many of these successful large language models. But the algorithm that was based on was like assuming that you're like say OpenAI who can train like humongous models, so which is not very like feasible for most people. But nevertheless, as long as you have the reward, we can still optimize for it. So I'll also go through our experimental results. So basically for few-shot classification, we outperform a number of previous approaches that either train the entire model or do various kinds of prompting, including using in-context demonstration examples. We still outperform them. So one concern that we might have here is that it still seems like a pretty difficult problem. You are optimizing over a search space that is as many as the number of stars in the universe. So you must be very inefficient, right? Turns out not so. We're in the figure to the right, we're comparing with the previous method that tunes these prompts not as words but as numbers, and it turns out we have basically the same efficiency in terms of how fast we optimize, and we converge to a higher performance. Here are our results for a text style transfer. So that's rewriting Shakespeare into modern English, or rewriting something in negative sentiment to a positive sentiment. Here, we also outperform previous methods that either train entire models or also use various kinds of prompting. One concern one might have is like, what if the previous methods that you talked about like are using much smaller models than what we're using? Actually, we're using the same model for all of these options right here. And also, we observe that sometimes the reward function might not be very stable, in that like for different inputs, it might have different levels of baseline rewards. So we developed some methods to stabilize this process. And as figure to the right shows, it really makes a difference. Actually, these methods are pretty generalizable. We applied it to the other tasks that we were running, and it uniformly improved the performance. So if you're using RL prompt, I will recommend that you try it out. And I'm happy to talk more about the details if you're interested. But here, I want to go a little bit into the analysis of what kinds of prompts we've been able to learn, because that's important to understanding like the utility of RL prompt. So what we found was that these optimal prompts are very good, even if they don't follow human language, and they actually perform better than human written prompts. However, these even if these prompts don't follow human language, they can transfer very well across models. That is, you can take a prompt, learn from one model, and apply it to many other models and get the same level, even better performance. So let me show you some details. So here are some examples of some manual prompts people have written versus our optimized prompts at the bottom. So you can see here that our prompts here are not coherent human text, but you can still look into it and see the patterns of what kind of words are preferred by the model for this particular task. Like for transferring from positive to negative, the model seems to like fixed, contrast, difference. Whereas for positive, it prefers comparison, excellent, parameters, experience. So also you can see that for manual prompt, even for like different phrasings of the same meaning of the same task, you have very wildly varying performance. Whereas across different experiment runs, we are pretty consistently among the best performance. So we have better consistency. You can also see that the manual prompts are pretty long, whereas our prompts are very short. So this will be beneficial for if you're interested in reducing latency or reducing the cost of running huge language models. Because on the latency side, because large language models will run slower when you have more when you have a longer like text in the input. So the shorter your prompt is, the faster the model will run, and the lower cost you will pay. So our method has this advantage. What's more, like I said before, one potential concern is that what if your prompt is just like pigeonholed into this specific model and it will not work on other models? Turns out it's not the case. So you can see here that we are taking our prompts trained with one specific model and applying it to all kinds of other models. You can see here that the performance stays basically the same. It can stay pretty constant across these models, and sometimes gets even better. This tells us that it's even possible for us to train a prompt using a smaller model and apply it to a larger model for better performance. You might also ask, perhaps a human written prompt can do better. Actually, the answer is also no. So if you see the figure on the right, at the top, we show the performance of manual prompt as they transfer across models. So they're actually not as good as the prompts that we learned from the language models themselves. So this implies that our method is able to better capture how these language models respond to prompts. So we've also been able to publish our code as a library on GitHub. It was pretty well packaged, so it's pretty easy to set up an experiment to quickly test some ideas if you're interested in using our framework. For example, this is other code that we wrote for running a text style transfer experiment. It took only 51 lines. The only thing really you need to do is to write a script to load the data and also to write a reward function, and we've taken care of the rest. And here's a demo that I have for a comparison between like not using a prompt using a human written prompt and using our optimized prompt. So the input here is ever since Joe's has changed hands, it's just gotten worse and worse. So it's a pretty negative sentence. What we want to do is to change it into a more positive sentence. So without the prompt, the generation is all over the place. And even with a prompt that seems reasonable, it's still a little bit weird. However, with our prompt, even though these are not exactly what a human will call a valid task instruction, nevertheless, the language model takes it super well. So it outputs a pretty good output. It generates a pretty good output that's turning the original sentence into a more positive sentence while keeping the original meaning. Yeah. So before I conclude, I just want to make sure that we can, if you are taking away anything today, nothing else today, please take away the following. So optimizing prompts for large language models is challenging, and it should be done carefully. The best way to talk to large language models is actually not necessarily human language. And reinforcement learning-based optimization can allow us to find out these best prompts more effectively. And if you're interested in more details, you can feel free to check out our blog post, or for more technical details, you can check out our paper. Or if you're interested in trying out our work, you can scan the QR code to the right for GitHub.